All right, part A, draw the free body diagram. All right, so this is the incline, that's the block. This is the horizontal force acting on the block. It's pushing the block up the slope, and so F fric for friction has to oppose that force, so it has to go down the slope. This is the force of gravity acting on the block. It's just straight down. And then this is the normal force of the surface acting up against the block. Normal force is always perpendicular to the surface, so that's why it's at an angle. And these dotted arrows here are the components of F and the components of Fg, which we will be using later. Part B, expression for the contact force that the incline exerts on the block. So I just started off writing the net force equations for the x and y direction. All right. So this is what I started off with. Net force in x, net force in y. So net force in x is this is the horizontal component of F over here, F cosine theta. And the reason we can say that the horizontal component of F is F cosine theta is because the angle of the incline here is theta. This is like a parallel line here, right? And then the horizontal force here is also a parallel line. Like, they are parallel, right? It's parallel to the bottom of the slope. And so the alternate interior angle identity of geometry says that when you have two parallel lines and they're intersected by a diagonal line like this, which would be the line of motion of the box, then the angles are actually the same, like here and here. And so this angle here is also theta, like this angle. And so that's why we can say that the horizontal component of F is F cosine theta. And then F fric and Fg sine theta, they are opposing it, they are pointing down the slope, and so that's why they're being subtracted. F fric, of course, is this right here, it's going down the slope. And then this angle here is actually also theta. And so since this horizontal component of Fg is opposite of that angle up here, then we can call that the horizontal component of Fg, which is Fg sine theta in this case, so it's sine theta. And then for the y direction, this is Fg cosine theta, which would be this part right here. It's just perpendicular to the surface, it's like going down into the surface. And then plus F sine theta, which is the downward force acting on the block from F here. It's this component right here. Minus Fn. Fn is the force up the block from the surface. And they amount to 0 because the block is not going up or down into the slope or into the air. It's just staying on the slope, so the net force in the y direction must be 0. And so from here, what we can do is we can bring Fn over to the other side. And we get that Fn equals Fg cosine theta plus F sine theta. And we can break that down further into Fn equals mg cosine theta plus F sine theta, because Fg is the same thing as mg. Let's see, part C. Develop an expression for the block's acceleration in terms of m, theta, f, mu, and g. Alright. So this would be dealing with it in the x direction, but we'll have both equations as well. So we'll just write down the x for now. Equation for net force in the x direction here. And then next what we'll do is we'll break down Fk. Everything else in the equation stays the same, but Fk can be broken into mu Fn. And then from there, we use our definition of Fn from the y equation here. Fn equals mg cosine theta plus F sine theta. Plug that in for Fn over here. So we get F cosine theta minus mu times mg cosine theta plus F sine theta minus mg sine theta equals ma. And then from here, let's see, I'll distribute the mu because we will need that structure of the equation for later problems. So distribute the mu over. Alright, so like here, just distributed the mu to both terms here. And then next, to just make it in a certain way that will be easier to solve in later problems, we can factor out the f and the mg from the terms that they're in. So just gather them next to each other first is what I'll do. Like that. Just rearrange the equation so that the f's are next to each other and the mu mg's and the mg's are next to each other, right? And then what we can do is factor out f from here and factor out the mg from these two. Like this. So factor out a negative mg actually, and so we have to put a plus sign in here so that if we were to distribute it, it would be back to a minus sign back here. And then from here we can just divide both sides by m. And so A equals F times cosine theta minus mu sine theta minus mg times mu cosine theta plus sine theta over m. Let's see. Part D. Develop an expression for the magnitude of the force that will allow the block to slide up the plane with constant velocity. What relation must theta and mu satisfy in order for the solution to be physically meaningful? All right. So for this one, this is where the arrangement of this comes in. So let's see. For the block to slide up at a constant velocity actually means that net force is 0, because constant velocity means that acceleration is 0, and if acceleration is 0, then net force must be 0, because net force is mass times acceleration. And so if the acceleration is 0, then the net force is 0 as well. And so this was the equation for net force right here, right? And so we can literally just set this part equal to 0. So here, just the same thing as this one, but we set it equal to 0. And then from here, to solve for f, we can just add this over. Like that. Just add it over to the other side to get this, and then divide by this. Just like this, right? So this is the expression for f. And as for the relationship between mu and theta, well, for f to exist, then this has to be greater than, greater than 0. Because, I mean, obviously, if the denominator of a fraction is 0, then it's undefined. It doesn't really exist. So this has to be greater than 0. So we can set this as an inequality. Oopsie. Cosine theta minus mu sine theta must be greater than 0 for f to exist. And then from here, we can just add mu sine theta to both sides. So cosine theta must be greater than mu sine theta. And from here, we can divide both sides by sine theta. Here, cosine theta over sine theta is greater than mu. And then this is just cotangent theta. So cotangent theta must be greater than mu. And if we want to get it in terms of like switch them around, then we can divide both sides by cosine instead. So like here we can divide both sides by cosine. We get this, right? And then this just simplifies to 1. And then the sine theta over cosine theta, that simplifies to tangent theta. So we get 1 is greater than mu tangent theta, excuse me for the big space in between. And then we can just divide both sides by mu. And so 1 over mu, excuse me, I don't know where that came from, must be greater than tangent theta. Part E, mass is 2 kilograms, the angle is 20 degrees, mu is 0.33, calculate the force required to accelerate the block at a constant rate of 0.5 meters per second squared. Alright, so we can just use the equation we found earlier, right here. Right, F cosine theta minus mu mg cosine theta plus F sine theta minus mg sine theta equals ma. In this case, ma is 1 because it's the mass, which is 2, times 0.5, which is just 1, right? And so the equation would be this. Just plug in all those values, and then you can solve. Alright, this is the equation with pretty much all the values plugged in, right? So theta is 20, mu is 0.33, mass is 2, g is 9.8, of course. And then there's an F in here, we're going to have to deal with that. And then this is just, you know, the mg sine theta. And then this is 1, because again, 2 times 0.5 is 1. And so what we can do is we can actually just multiply all of that stuff out to get the F here outside the parentheses, so we can combine it with this F here. And so we're gonna have to do that with our calculator, actually. So all right, so if we do that, and then just do the last little part here. All right, so after it's all been done, F cosine 20, and then minus 0.113F, because that's what you get when you multiply this by this, and then multiply this by this, and you get 6.078, and then this here is just 6.7. Set that all equal to 1, combine the F's here. You get combine the F's here, you get that, and then just add these to both sides. You get that, and then just divide both sides by 0.827. And you get F equals 16.66 newtons. Right there. Part F, additional block of mass 4m. Drive an expression for the magnitude of the force required to keep the system motionless. All right. So motionless. So let's imagine it as one big block with mass 5m, right? Because there's already one mass of just 1m, and then we add 4m to it, that's 5m. So one big block with mass 5m, and because they are on the slope, they naturally want to move downward. And if the system is motionless, that means that the force is keeping the horizontal force is keeping them up, but also the friction is keeping them up, because they naturally want to slide down, and friction acts against them. So we add friction and the applied force rather than subtracting. And so the equation looks like this. Okay, right here. The horizontal component of the force plus this whole thing is basically just the force of friction. This is the normal force because the normal force is the only upward force acting on the two blocks. And so it has to equal in magnitude to the two downward forces acting on the two blocks. Because there is no acceleration in the y direction, multiply all that by mu, and then we set it equal to the gravitational force that wants to pull the blocks down the slope, which is just 5 mg sine theta. And so we can just add to both sides, or subtract to both sides, excuse me, made that mistake again. Right, like this. And then we can divide by cosine theta. So we get F equals 5 mg sine theta minus mu times 5 mg cosine theta plus F sine theta over cosine theta. G, if mass is 2, angle is 20, mu is 0.33, calculate the force required to accelerate the blocks of the ramp at a constant rate of 0.5 meters per second squared. All right. We can just treat this like, sorry, I forgot I had a new paper. We can just treat it like this problem right over here. Just the same structure, basically. And so we can say F goes, oh, and this time friction is going down, so we subtract it from the force. Let's see, 5m times 2 would be, 5 times 2 would be 10, because m is 2. And so the net force would be 5, because it's accelerating at 0.5 meters per second squared. 0.5 times 10 is 5. And so this is the equation. F cosine 20 minus mu 5 mg cosine 20, plus F sine 20. I almost wrote an equal sign here. Forgive that. Minus 5 mg sine theta. That's a 20. Equals 5, because again, 5m is the total mass. M is 2. 5 times 2 is 10. And then it's accelerating at a rate of 0.5 meters per second squared. 0.5 times 10 would be 5. And so we can just work that all out and plug in the given values. Then that should be okay. So we get this, right? So this, and then together with this, that comes out to 63.91. And then 0.33, which is mu, times sine 20 would be around 0.113, and so we just put f to that. We can put these together and then add 63.91 on both sides, and we get f. So we get F equals 83.34 newtons. So get that, right? And then 0.827, because sine 20 and then 0.113, they come together to make 0.827F. And then just add this to both sides, you get 68.91, almost at 31, excuse me. And then just divide by 0.827 and you get around 83.34 newtons. Part H, let me draw the diagram out first, make it a little easier. This is the diagram. Here we see that this is F, these are two boxes. So technically, the only force that's actually touching 4M here, besides friction, of course, is the contact force coming from box M over here. And so that, if we want to find the contact force, then we should focus on that box. And also the contact force would be the only positive force for that box as well. Excuse me. This is the equation for the top box over here. Contact force, it's the only positive force, minus the frictional force, which is just mu times the Fn of that block, and then minus 4 mg sine 20, which is the gravitational force trying to pull it down. And so, excuse me, set that equal to the net force, which is mass times acceleration. 4m is 8, and then acceleration is still 0.5, so it's all going to be equal to 4. And then just plug in those values. All right. So we get this. All right. So just plug in the given values, and all of this stuff adds up to 51.13, and then add it to 4. Can't believe I just used a calculator for that. .13 newtons. Oh, all right. So that's a contact force. And then part I, student claims that switching to whatever that box is does not affect the magnitude of the contact force. Okay, so I disagree. And the reason I disagree is because, let me draw the thing in a bigger way this time. the reason I disagree is because the contact force entirely depends on the box that is on top. And by on top, I mean the box that is not being directly acted upon by the applied force. So in our previous case right here, the contact force was this, but that entirely depends on the box here. If the box were not there, obviously there literally would be no contact force. If we were to switch these around, like this, the contact force would change because they're switched around. This, again, the contact force entirely depends on what box is on top. If the lighter box is on top, then the contact force will actually decrease because the lighter box will be pushing against the heavier box with less force, because there's no way it would be pushing on with more force if it weighs less. And we can do the math for that right now. So M is 2, acceleration is still the same. This would be the equation if M were on top rather than 4M. So the contact force from 4M to M minus the frictional force on M. So this would just be mg cosine 20, right, for the Fn. And then this would just be mg sine 20 for the gravitational force acting on M, equals 2 times 0.5. That's 1, because M is just 2. And acceleration still stays the same. Plug that in. We get this, right? And then just add negative 12, add 12.78 to both sides. Don't need a calculator for it this time. If we were to switch the boxes around, as you can see, the contact force would decrease significantly. Excuse me. Put an N at the end. If we were to switch the boxes around so that the lighter box were on top instead of the heavier box, the contact force would decrease significantly, because again, the contact force entirely depends on what box is on top. If the heavier box is on top, then the contact force will be bigger. If the lighter box is on top, then the contact force will be smaller. Thank you.